Okay, welcome back everyone. And up till this point, we've been looking at first order models. So, in this video, I'm gonna start our discussion about second order models. And to start off, I'm gonna take the example of a physical mechanical system, a mass spring damper system, which is usually very commonly encountered in an engineering vibrations class. So let's suppose we have a spring with stiffness K. We have a mass we have a block of mass M attached to the spring, and we have a mass damper with a damping constant B. Okay, and there's an applied force which is going to be a function of time that's going to pull the mass to the right hand side, and we need to develop a model for this block right here in order to predict the position of this block at any given time. So this is done by applying Newton's second law, and we all know that acceleration is the second derivative of position. So we're gonna have mass times acceleration on the left side, and let's see, we have the restoring force k times negative k times x, and we're gonna have the damping force negative b times the velocity, which is the first derivative of position, and then we have the applied force, which is pulling the mass to the right hand side. So the right hand side of our equation becomes f of t minus k of x minus b times dx dt. So rearranging all of our x terms on the left hand side, we get m times the second derivative plus b times dx dt plus k of x, and that equals the forcing function. Alright, and let's divide everything by k. Alright, so we're left with m over k times d square x dt plus b over k times dx dt plus x equals f over k. I'll just write this as 1 over k times the forcing function, because f of t, this can take many forms. This can be a periodically varying force, this could be an impulse, this could be a step function, so this could take many forms. Hence we'll leave it in its most general form. Okay, so as we did earlier, the first term, we're gonna rewrite this as the time constant squared times the second derivative. The second term becomes 2 times the damping factor known as eta times tau dx dt plus x, and all of that equals the gain of the process k times f of t. So from a physical standpoint, for a second order model, the time constant tau, the damping factor eta, and the gain of the process, they all derive their physical significance from a vibrating system. So from basic intuition, even if somebody does not have any detailed knowledge of classical mechanics or physics or has never studied vibration theory, they know that if they're going to pull a mass, they're going to have an oscillatory response, and eventually that response is going to decay out, it's going to damp out, and the harder they're going to push it, the more aggressive the nature of the oscillation is going to be. And that's how second order models are generally characterized. They're Most second order models are understood by the analogy of a vibrating mass spring damper system. Okay, and one important thing that is worth noting is that for first order models, remember that it was tau was the time taken to reach 63.2% of the total change in a step response. However, in this situation, that's not the case. So be careful when you're dealing with taus in a second order system. And let's suppose our initial conditions for this process were 0. We had 0 initial conditions. Our initial position was at the reference, and we were starting from rest. Okay, so if you have boundary or initial conditions that equal 0, they're also known as homogeneous initial conditions. So if you encounter the term homogeneous boundary condition or homogeneous initial condition, that just means that the position at that time or the derivative at that time is going to be equal to 0. And let's say, for example, we take a forcing function. We take a forcing function that represents a step response. So initially there was no force, and suddenly at t equals t naught, we there was a sudden increase in the force. Let's call that, we're gonna call that f naught. So the total change in f was delta f equals f naught minus 0 equals f naught. Okay. We have studied the response of a first order system earlier. Now we're gonna look at the response of a second order system and the parameters that are going to be critical in this response. So once again, the object was initially at its mean position 0, and then at t equals t naught we had our disturbance. And since this is going to be a higher order response, we can have three possible curves. We can have something like this. Okay, let me just make that a little bit more prominent for you. And yeah, okay. We can have something that is slightly, hold on. We're gonna have a response that is slightly more similar to a first order response. Looks something like this. Okay. And on the And finally, we can have a response where the position shoots up for a moment before finally coming down to its new steady state. So these are the three possible types of response you can encounter in a second order system. Now, the response highlighted in red is known as overdamped response. The response in gray is critically damped. And the response in blue is underdamped. So, since when a process is underdamped, it will usually exhibit a tendency to overshoot and oscillate before it reaches its final stable position. So, from a stability standpoint, a critically damped system is the most desirable state. And the different degrees of damping in a second order model are controlled by the value of the damping constant eta, this right here. So in the case of a, now since we're doing our discussion on a mass spring system, the value of this term right here should be equal to B over K. So 2 times eta times tau must equal the damping factor over K, where the value of eta and the value of tau squared was equal to m over K. Tau becomes equal to mass of square root of mass over K. So by solving these two equations, you'll find out that the damping factor for a mass spring system will be equal to 1 over 2 times B over K times square root of K over M. Okay, if the value of eta is equal to 1, we're gonna have a critically damped system. If eta is greater than 1, we're gonna have overdamped system, and the response looks something like the one that's shown in the red curve. And if it's below 1, we're gonna have an underdamped system, so we're gonna have an oscillatory response which has a tendency to overshoot the final steady state. Alright, and once again the change in x here, the delta x will be characterized by the sensitivity or the gain of the process. So if you multiply k by the total change in the forcing function, you'll be able to find the final steady state position of your system. So the gain has the same definition for first order models and second order models. Now we discussed the significance of the damping factor eta, and for a higher order system, tau is just going to tell you how fast slash slow the system is. We won't have a nice precise definition like we had earlier in a first order system. So this pretty much sums up our discussion for a higher order system. And for most problems in this course, you will not encounter models that have a higher order than 2. In the next videos, we're going to look at a Laplace transform treatment of higher order models. So stay tuned.